Look at the sheer physical scale of this landscape. It is a massive, unforgiving environment. Finding anything hidden beneath it requires extreme precision. Geoscientists see this landscape as a sequence of discrete data points. The orientation of a ridge or the specific hue of a rock face reveals the tectonic history of the entire region. The outcrop analog principle allows us to bridge the gap between the visible and the hidden. We treat these exposed formations as a physical record of the deeper layers, assuming the geometric properties we see here continue downward for miles. Take the Tuwaic escarpment, for example. We use these exposed rock formations as a direct proxy dataset. By studying the porosity, permeability, and fracture networks of these rocks right here on the surface, geologists can accurately predict how the exact same rock layers will behave when they are trapped deep within the Earth's crust. Understanding the physics at the surface is the absolute prerequisite to decoding the hidden subsurface architecture, where oil actually resides. Extracting that data starts down at the human scale, directly in the field. This is a Brunton compass, the foundational analog tool geologists use to measure the exact orientation of rock beds. This diagram shows two critical metrics. First is dip, the specific angle a rock layer tilts downward from a flat horizontal plane. Second is strike, the horizontal line created where that tilted rock intersects the plane. A single measurement tells you very little, but when geologists plot hundreds of these localized points across a map, massive regional structural bending starts to appear. Occasionally, the mapped dip measurements will consistently point outward and away from a central linear axis. This diagram shows what that pattern creates, an anticline formation. The outward-facing arrows at the surface directly correlate to a convex, dome-like trap below ground. Hydrocarbons naturally migrate upward through porous rock, making this convex dome shape the ideal geometric trap to capture and hold large accumulations of oil. Those raw, localized field measurements are the first direct indicators pointing us toward high-probability deep oil reserves. Manual field mapping provides incredible accuracy, but it is functionally too slow to cover the required territory. Exploration targets are massive. A target like the Arabian Shield covers over 600,000 square kilometers of rugged terrain. To solve this geographical scale limitation, geologists have to pull their perspective back into orbit. Short-wave infrared, or SWIR sensors, capture reflected light beyond the visible spectrum. These satellites isolate the specific spectral signatures of surface minerals, allowing us to categorize rock types from orbit. The precision is remarkably high. We can map key surface geology like carbonates and clay minerals down to a 10-meter resolution from hundreds of kilometers up. But there is a critical limitation. SWIR perfectly maps exposed minerals, but it becomes completely useless if the target geology is buried beneath environmental cover. This brings us to the specific geographic challenge found in extremely arid environments like the Rub al-Khali. We call it the sand sheet problem. Millions of tons of dry aeolian sand visually obscure the underlying bedrock and any tectonic structures it holds. Standard optical and infrared satellites cannot see past this superficial layer, leaving geologists with a massive data blind spot. The solution is synthetic aperture radar, or SAR. This specialized remote sensing technology is capable of physically penetrating dry, dielectric sand. This diagram illustrates the physics. A radar pulse travels from the satellite, hitting the surface at a 50-degree angle, passing straight through the wind-blown sand. Underground, the signal interacts with the hidden environment, reflecting off the eroded bedrock interface and fluvial deposits before bouncing back. These scattered radar signals expose what we call lineaments, deep-seated faults and paleochannels that are entirely invisible to the naked eye. Mapping these hidden lineaments is vital because underground tectonic cracks serve as the primary migration pathways for hydrocarbons, moving from source rock to a reservoir. Field surveys, multispectral mapping, and SAR radar generate vast amounts of data, but they are insufficient in isolation. They must be algorithmically combined. This data integration occurs within a Geographic Information System, or GIS environment. This model shows how the integration works. We start with the foundational base layer, the topography, mapped as a digital elevation model. Next, we layer the ground-truthed field data, specifically the physical strike and dip vectors, directly onto the topographical basemap. Then, we slide in the orbital multispectral data, laying out the precise mineral compositions over the vectors. Finally, we drop in the SAR-derived hidden fault lineaments, completing the stacked data matrix. When we look for intersecting anomalies across all these disparate layers, the software highlights high-probability geographical zones. We call these prospects. This integrated 3D model successfully transforms abstract geological data from space and the field into a concrete, actionable exploration target. This theoretical matrix connects directly to historical hydrocarbon discoveries. The Dammam Dome serves as a case study for this approach. Mapping the surface structural expression here was the direct precursor to the development of a world-class oil field. The core economic imperative here is risk reduction. Surface mapping acts as a massive spatial filter, designed strictly to eliminate bad exploration bets before heavy spending begins. This phase does not extract a single drop of oil. It dictates exactly where to allocate the massive capital required for the intensive steps that follow. The Earth never lies about its history.